Hello, welcome physics students. Today we're going to be taking a close look at the work-energy theorem and how we can use the ideas of the work done on an object is connected to the change in energy of that object to solve for some problems including force and distance traveled during that exchange of energy. So stay tuned. We're going to be taking a look at a couple close problems. Please have your notes ready and add some key concepts along the way. Thanks. Okay, to help us examine this relationship between work and energy, we're going to take a look at a rubber band and how it is attached to a block that's pulled back and stretched. And you can kind of see that over here. This is where the block would be pulled back and stretched to this initial position. And then the block is released and it slides across the floor until it comes to a stop. And so we know that the distance it moves is going to be this 2.5 meters. That's this distance here. And we're going to figure out that it is actually stretched back from here to here. We know that distance is 0.1 meters. So we're going to have to figure out how to use that relationship and those two distances. The relationship we're going to focus on is the energy required to stretch back the rubber band stores up all the energy, and that's given to us by 1/2 k x squared. And that's equal then to the force times the distance, or the work done by friction in order to stop this. I'm going to put some numbers in. I know that the K value for this was 105 newtons over meters, and the distance stretched was 0.1 meters. And then I'm going to plug in the value for the force of friction, we'll solve for the force of friction, but we know the distance that it was actually sliding to a stop. That's the 2.5 meters. The key thing about this problem is knowing which distance to put where. When we solve this out, we now know the force of friction is 0.21 newtons. That's great, but we want to find out the coefficient of friction. So we have to go back to our force relationship where the force of friction is equal to the coefficient times the normal force. And in this case, the normal force is equal to the weight of the block, which is mass times gravity. So our coefficient equation then, we can start substituting in. We know the force of friction is this 0.21 newtons times the coefficient. We need to solve for that, but we know the mass of the block and we also know the acceleration of gravity. Now I can simply solve for coefficient, and I'm going to end up with about 0.107 for my coefficient of friction between these surfaces. Notice how we use the relationship between energy and the work done in order to set up the equation and solve for that force of friction. Then knowing force of friction, we went back to solve for a coefficient. Another great example of this work and energy theorem working together to help us solve some problems is a diver that might be going off of a high dive and then landing in the water and coming to a stop in the water. So when we identify the energy relationship here, we know we're going to have a certain energy at the top, and that's equal to the work done by the water to stop them. So the stored energy is all potential energy. It would be equal to the kinetic energy at the bottom, but that's an extra step that we really don't need. We can reduce that down to just the stored energy at the top. The potential energy is equal to the work done by the water, the force of the water times the distance traveled in the water. I now can substitute in. I know the mass of the diver. I know the acceleration of gravity. I do know the height, and I'm going to solve for the height. I'm looking for how high that the diver fell in this case. I know the force of the water was 1,500 newtons, and I know the distance that that force acted over was 4 meters. Substituting in, now I can now solve for the height of about 12.2 meters. Thanks.